Good morning once again. I know this can be a very boring subject for people who are not good with their numbers, but if you like numbers, uh, I hope you'll enjoy the session, and I'm going to try to make it as simple and as fluid as I can. And once again, I would like to say welcome to our hospital, Anadolu Medical Center. Today I will be presenting this subject, and it will refresh hopefully your memories um, on the very basic terms and equations we most often use in our routine practice in a molecular laboratory in procedures such as DNA extraction and PCR amplification and also gel electrophoresis. The main topics I will go over will be centrifugation, units of measurement, concentration, molarity, and X factor. Our learning objectives in this session will be to convert centrifugation units to each other, to convert measure units to each other, to prepare the required concentration of a lyophilized solution, especially our primers, to prepare a solution of low concentration from a solution of high concentration, and also to dilute concentrated solutions. And hopefully at the end of this session, we will all be able to calculate and fill in for all those question marks you see there. This is an example of a PCR setup, and on the left column you see the components of our PCR setup, and the right column shows the final concentrations we require. So let's start with centrifugation. Important things about that we should not miss. Centrifugation, as we know, is a process that involves the use of centrifugal force for the sedimentation of mixtures in a centrifuge. So by this process, we try to separate particles of different masses. And the two terms that we most often use related to centrifugation is one, revolution per minute, and two, G. Our revolution per minute is RPM, and G is relative centrifugal force. And if you look at the equation below, we see that G is directly proportional to the radius of the rotor of the centrifuge. What does this mean? This means that at the same RPM, if we use rotors of two different radiuses, the sedimentation rates will be different. So what we should be careful about is, if we use, in our terminology, RPM, revolution per minute, we must state together with that the radius of the rotor so that it can be, so that our G can be calculated. And we can do that using this equation, or more easily using a standard nomogram like this one. Say we have a rotor radius of 75 millimeters and an RPM of 2,500. We see that our G would be 500. And passing on to my second topic, it is the units of measurement. Units of measurement, we know that there are 7 internationally acclaimed units, but we are mostly involved with these three: mole, meter, kilogram, and also one more unit which is derived from all of these three. I'm not going to explain the definitions of all these three, but try to give you some examples and try to highlight where we can make mistakes with this subject. If we want to measure the weight of the Earth, we would use a unit like iota, whereas we want to measure the weight of a proton, we would use yocto. So one subject where we should be careful about is the same letter can be used for two different units. So even using a abbreviation with a capital letter or not makes a big time difference. In routine lab use, we are mostly involved with milli, micro, nano, and pico. And I would also like to note that even between the two nearest ones, let's say micro and nano, there's a 1,000-fold difference. So making a mistake in our calculations would cause a 10,000-fold mistake everywhere in our analysis. Let's have an example, a small example. There are a couple of examples of different units and how they are converted to each other. But let's try one example. Let's say we want to convert 1 grams per liter into milligrams per deciliter. What we should be doing is, first we take the grams, denominator, and convert it to milligrams, and it would be 1,000 milligrams. Then we take the denominator, liters, and convert it to deciliters, and that would make 10. Then what do? We divide the numerator by the denominator. So 1,000 milligrams per 10 deciliter would give us 100 milligrams per deciliter. My third subject is concentration, percent mass, and the conversion of units in concentration into each other. Let's first remember the definition of solution. A solution is a mixture which is composed of a dissolving phase called solvent and one or more dissolved phases we call solutes. So concentration is a measure of how much of that solute is dissolved in a solvent. And the two units of concentration we use mostly in the lab is molarity and percent. When we say percent, that means the amount in total volume is defined in terms of percent. And there are two types of this. One is percent weight per volume. This one we use mainly for solids dissolved in liquid phases. And the second one would be percent volume per volume. And this one we would mainly use for solutions to be diluted. And the equation is percent volume, mass of solute per total volume of solution times 100. So using this equation, let's exercise with preparing two examples. One for percent weight per volume, preparation of 50 milliliters of 2% agarose, which we would be using in a gel electrophoresis, and preparation of 500 milliliters of 70% ethyl alcohol. So when we put these in our formula, we want to prepare a 2% solution. We don't know how much we should be weighing, but we know that we want to prepare a 50 milliliter solution. So everything put in place, we find that we need 1 grams of agarose to make this solution. We could, if we forget the formula, we could always, of course, use a direct proportion and say, if we have 2 grams in 100 milliliters, how many grams should I have in 50 milliliters? So we could come up with that easily in another way. And then we take 1 gram of agarose and dissolve it in 20 milliliters of our solvent. So far, things go simple. Let's hope to keep them that way. Let's try another example. This would be preparation of 500 milliliters of a 70% ethyl alcohol. Again, we know the percent of ethyl alcohol and we know how much we want to prepare. So we're trying to find out how much of alcohol should we put. And in the formula, we find that the result is 350 milliliters. Again, we can do it a lot easily using direct proportion. So what we will do at the end is we will take 350 milliliters of ethyl alcohol and we will add on top 150 milliliters of water to make it a total of 500 milliliters of a 70% ethyl alcohol solution. Next subject will be molarity. Molarity is the concentration of a solution. The concentration of a solution is most commonly expressed by molarity and defined as the number of moles of dissolved substance per liter of solution. What we should be careful here is that when we say molar, we always mean grams and liters. So let's go on to what a mole is. A mole is the mass of a dissolved substance expressed in grams divided by its molecular mass. And the molarity of a solution would involve three constituents. One of them is the weight of the substance in grams, always in grams. The second one would be the molecular mass of the substance, and the third one would be the amount of the solvent. So, the one thing we wouldn't maybe know here would be the molecular mass of substance. But of course, as we all know, it's very easy to find that from Mendeleev's periodic table. When you look at any element, the number on the left-hand corner would show the molecular weight of that element. And examples for molecular weights of some of the very common elements. For example, hydrogen, we know it's 1, oxygen is 16, sodium is 23, and so on. So again, let's go to another example. Let's try to prepare, this time, a 0.1 molar sodium hydroxide solution, and let's prepare 500 milliliters of this. Using the molarity formula, we first find the number of moles we need. We know the final molarity, we know the final volume, but we don't know how many moles do we need. So we first calculate that, and it's 0.05 moles. But of course, we need to weigh this sodium hydroxide. So we also need to know the atomic weight, molecular weight of sodium hydroxide. And how do we calculate that? It's 23 for sodium and 16 for oxygen, 1 for hydrogen. So the total molecular weight of sodium hydroxide is 40. How many moles did we need? 0.05. So the amount of sodium hydroxide that we need to measure would be 2 grams. And then in a volumetric flask, we have to fill it up to 500 milliliters. One thing we should be careful about is that we shouldn't fill it up to 500 milliliters immediately when we are back there in the lab. We should first dissolve the 2 grams in a smaller amount and then fill it up to 500 milliliters in the volumetric flask. Let's try a more specific example that we could use in the molecular pathology laboratory. In such a lab, we would have to dilute sometimes a lyophilized oligonucleotide, for example, a 3.6 nanomole oligonucleotide. And let's say in the final mix, we want a concentration of 50 picomoles of oligonucleotides per microliter. We would again use our formula. So we would find that we need 72 microliters of our oligonucleotide. We would need 72 microliters of distilled water. If we take our lyophilized sample and add 72 microliters of distilled water to this primer, we would have a final concentration of 50 picomoles of primer in 1 microliter. We can again do that using direct proportion. Another area in lab math is the changing of concentrations to preparing a low concentration solution from a high concentration solution. Here again we have a very simple formula. The concentration of the first solution and the volume of the first solution equals to the concentration of the second solution multiplied by the volume of the second solution. Let's again explain this with a simple example. Let's say we want to prepare 100 milliliters of 40% alcohol from a 70% alcohol. What do we know? We know our concentration of the first solution. We have a 70% concentration. but we don't know how much of it we should use, so we don't know V1. We know the concentration 2, it is 40%, and we know the final volume, it is 100. So simply by putting it in the equation, we find that the volume we need is 57.14 milliliters. How do we do that? We take a 57.14 milliliters of 70% alcohol, and we just fill it up to 100 milliliters with distilled water in a volumetric flask. Again, let's try a more specific example for the molecular mass. How much of a 10 millimolar DNTP mix solution should we use to reach a final concentration of 200 micromolar in 550 microliters of the master mix? So what do we know here? We know what we are trying to find is V1. How much of this is what we are trying to find? Here, one thing I'd like you to be careful with is one of them is millimolar, the other one is micromolar. So here we should not make a mistake, and we should not forget to convert these two into each other. And then when we put our numbers in the equation, we find that the amount we need to take would be 1 microliter. We take 1 microliter of the 10 millimolar DNTP mix. We make it to a final concentration of 200 micromolar in the 50 microliter master mix. The final subject I will go over is the X factor we see. Now, X factor, in labs we usually use stock solutions, and we maintain them as more concentrated solutions, and we dilute them to working strength when we use them in our typical applications. And usually the working concentration is denoted as 1x. So a solution 20 times more concentrated, in this case, would be denoted as 20x. And to make it a 1x working solution, we would have to dilute it to 1 to 20 and restore our typical working concentration. This is again an example of a PCR setup. Let's say in this setup we use a 10x PCR buffer, and the final working concentration we have said would be 1x. How much of this should we use for a total volume of 100 microliter mix? We should be taking 10 microliters. Again, we use the concentration changing formula. We know we don't know the first volume, but we know the final concentration. And then the second volume, total volume, is 100 microliters. So when put in the formula, we can easily see that we will take 10 microliters of the PCR buffer. Now let's get back to this very first slide I have shown. I said we would like to calculate at the end of this session, and I'm almost finishing my session, the question marks. Let's go over each of them. In this specific mix, we need a 1x buffer. So what do we do? The final concentration would be 1x. The total volume is now, this time, 50 microliters. So we will do 50 divided by 10. We need a 5 microliter of the buffer in our PCR setup, in our PCR mix. The second one, we need to make, we have a 25 millimolar magnesium chloride, and we need to have in the final concentration 2.5 millimolar. So we know that the concentration 1 is 25. We don't know the V1, how much of that we should take, but we know the second final concentration, and the final volume is, as shown at the bottom of the slide, 50 microliters. So 2.5 times 50 divided by 25, we see that we should be taking again a 5 microliter of the magnesium chloride. For DNTP, a 10 millimolar DNTP, again using the same formula, but again not forgetting to convert the millimolar to micromolar or vice versa. If we change micromolar to millimolar, which would be easier, we would have 0.2 times 50 divided by 10, so that would make a 1 microliter. How much of primer A should we have, should we weigh for the final concentration of 0.2 micromolar? Here we use the molarity formula, because first we have to find how many moles of primer A we want to use. So again, we know the final molarity, 0.2, and then we don't know how much we should take, but we know our volume, 50 microliters, and the equation comes up with a 10 picomole. But how much does this 10 picomole make? We need to know also the atomic weight of our primer, and this we can find now. This we can find in the inserts of our primers. So let's go back. Sorry. Again. To primer B, it's the same as primer A. We use a molarity formula. We know the final molarity. We know the final volume. We find out how many moles of primer B we want to put in the solution. Then again, using its molecular weight, we find how many grams, milligrams we need. In this case, it is 0.061 microgram. And then when we pass on to DNA polymerase, we have a DNA polymerase of 5 units per milliliter, and in the reaction we want only 2.5 units. So we need to take only 0.5 milliliters of that DNA polymerase. The template DNA we can weigh, we know the weight, and let's say ours is 2 nanograms per milliliters, and in the final concentration we want 20 nanograms. So we need to take 10 microliters of the template DNA. So now that we know how much in volume and in mass of the constituents of the components we will put in the final mix, we fill the rest with up to 50 milliliters, and we will have our PCR tube. So hopefully subjects, maybe a boring subject such as this, has been very quick, very fluent and understandable, I hope. And I wish you all the best with your lab math in the hands-on practice you will all go through. Thank you for listening to me.